Hello everyone, welcome to this video lecture. In this lecture I am explaining how to write a verilog code for ripple carry counter, and let us simulate the ripple carry counter module and let us see how to simulate the counter with different input values. So in the design you can observe the block diagram here. This is the ripple carry counter which is taking an input of clock and reset, and Q0, Q1, Q2, Q3 are the outputs here. So in this design you can observe T flip-flop are the submodule I have used. Means by using T flip-flop I have built a ripple carry counter, and these T flip-flops are going to operate with negative clock cycle. Means at the negative clock cycle the output of this T flip-flop is going to be generated, and the name of these instances are TFF0, TFF1, TFF2 and TFF3, and this T flip-flop is designed again by using D flip-flop. Okay, now let us see how to write a verilog code for this. So in the design part, module is the keyword, ripple underscore carry underscore counter is the name of the module here, and the output is Q, clock, reset are the inputs. Output 3 is to 0 Q. Because of Q is a 4-bit output, I need to take this Q as vector, so 3 down to 0 is taken. Similarly, we have two clocks, so clock and reset are single bit inputs, so input declaration of clock and reset is made here, and then I need to instantiate this T flip-flops. So 4 T flip-flops are there in a ripple carry counter, so I need to instantiate this T flip-flop 4 times, and I need to map this input and output of the T flip-flops to the input and output of the ripple carry counter. So the first T flip-flop with the name TFF0 is instantiated here with the name TFF0, and Q0 is the output, clock and then reset. Similarly, 4 T flip-flops are making our design of ripple carry counter, and here you can observe T underscore FF is the module which I have instantiated, and the code for that is written over here. This is the code which is representing a T flip-flop where it is designed again using D flip-flop. By instantiating D flip-flop we have created T flip-flop. Okay. For this design we require one more device, that is NOT gate. The NOT primitive is used here. So again D underscore FF is a another module which is instantiated over here. So for the D underscore FF I have written the code over here. Okay. So this is how we can write the design of ripple carry counter. Okay. Now let me write the test bench for this design. I need to check the functionality of this design by giving the input values. So for that I have written the test bench here. This is the code of test bench. You can observe module stimulus, name of the module is taken as stimulus. Here we have clock, reset as registers, and wire 3 is to 0 Q. Okay, these are the variables I need to declare as register and wires, and I am instantiating this design block. The top design block is ripple carry counter, so ripple carry counter, and then R1 is the name of the module or the name of the instance. This is the name of the module and R1 is the name of the instance here. Q comma clock comma reset in the same order what I have followed here I have written, and then I am taking the values like this. Initial clock is equal to 0, set the value clock to 0 first. Always #5 clock is equal to not of clock, means for every 5 time units this clock value is going to be inverted. Okay, so I have generated clock here. From this to this line I have written the code for clock generation. Okay, and then I need to assign values for reset. Initial, begin, here is the initial block, that's why I am using begin and end. In between begin and end under initial, if I write the multiple statements, this constitutes an initial block. So reset is equal to 1 initially, and then after 15 time units of delay I am making reset as 0. When reset is 0, my counter is going to start counting the values, right? That's why I am giving a large delay in between the two statements, like reset is equal to 0 and 1. In that time period it will start counting from 0 and it will reach 1 1 1 1. Okay, the sufficient time is given over here. Why? Because for every 5 time minutes the clock will change. Okay, For every 10 time minutes, I am going to get one more count. Okay, and then to check the functionality whether it will reset, I am giving here reset is equal to 1 after 180 time minutes, and then again reset will be 0 after 10 time minutes, and then after 20 time minutes of this particular time, the simulation is going to be terminated. And to monitor the outputs, to display the outputs in the console window, I have used $monitor. Okay, and then within that I am displaying a simulation time, and then the value of the clock means in binary, and also reset, and then output. Okay, so this is what I am trying to display in the console window. If you run this particular code, you can observe when reset is equal to 0, it start counting. It will start counting from 0, 0, 0, 0, and it will reach up to 1, 1, 1, 1, and then reset becomes 1, and again it will be reset back to 0, and it will start counting. Similarly, if you look at the next values, again reset will be 0, and then it will start counting. Because of $finish we have used after 20 time minutes, the simulation is terminated. Okay, this is how the counter design can be made, and the values can be given in the test bench to check the functionality of different set of input cases, and you can check the working of this particular ripple carry counter. Thank you.